So that's a lot of theory. So let me actually now let's get into the example. So let's say I have this guy. This is a graph of f of x equal x cubed minus 6x squared plus 9x minus 4. Okay. Now, well, let's see. I'd like to determine whether the intervals on which my function or my derivative has the following property. So first one, my function is positive. Let me see. So once again, positive means it lies above the x-axis. So my function is positive from on the interval 4 to 5. My function is negative when it lies below the x-axis. So it's negative on the interval 0 to 4. My function is going to be increasing when it goes up. And you can see that it goes up here from 0 to 1 and from 3 to 5. Wait, it's actually to 4.5. So from 3 to 4.5. So my function is going to be increasing from 0 to 1 and from 3 to 4.5. Let me actually change this to 4.5. And a function is decreasing when it's going down. So a function is going to be decreasing on the interval from 1 to 3. So, well, I have the graph. So these guys are pretty easy to spot. Now then, I need to know the interval where the function, where the derivative is positive. But if you remember, the derivative is going to be positive when the function is increasing. So these two guys are actually the same thing. The derivative is going to be positive when the function is increasing. So this interval are going to be just the same thing. And same deal with the other one. My function is going to be decreasing when the derivative is negative. So my derivative is going to be negative on the interval from 1 to 3. Now, for part B, if I were to draw the graph of f of prime of x on the axis here, well, what information do I know about the derivative so far? I know that it's going to be positive from 1 to 4, I mean from 0 to 1, and from 3 to 4.5. So that means my derivative should be positive, it should be above the x-axis on this interval. It should be below the x-axis, it should be negative on the other interval, which is 1 to 3. So basically, this is what's going on here. I look at the graph of my function. I see that it's increasing on the red piece. So the red piece is going up, so it's increasing. Because it goes up, that means the derivative has to be positive. Because the derivative has to be positive, I knew that it has to lie above the x-axis from 0 to 1 and from 3 to 4.5, which is the red interval that I have. Now then, my function goes down from 1 to 3. Because it goes down, derivative is negative. Because derivative is negative, the derivative, if I were to draw the graph, it has to lie below the x-axis at that point. So I don't know anything about the derivative yet, but I knew that it has to lie above the graph here, lie below the graph here, lie above the graph here. So in my case, if I have to draw the graph, it should look something like this. It should be somewhere here, it crosses the axis down here, stay down here, and it goes up here. So if I were to draw something like that, that will satisfy my condition. So let me do that. Let's say it should look something like this. Actually, let me draw. Show up. So notice how this actually satisfies the condition that I have. It lies above the x-axis on the red interval. It lies below the the x-axis on the green interval. So there's no way I can be exact at the moment, so I'm gonna leave that as the answer for now. So let me now do my part C. I like to determine the interval on which f prime of x has the following properties. I like to know when my function concave up. So again, concave up look like a cup, concave up look like a U, and my function look like a U around here. Maybe I should erase this guy. Okay. My function look like a U here. So this pink piece is when my function is concave up. So it looks like a U when it concave up, and that's going to be from 2 to 4.5. And it concave down when it looks like an N. So my graph concave down on this other piece here, from 1 to 2, from 0 to 2. So this part is concave down. And they did not ask, but let me say it anyway. This guy, this is going to be the inflection point. Now then, notice how this actually coincides with the answer here, because we knew that my function concave up when my derivative is increasing. I said that my function concave up from 2 to 4.5, so my derivative, it better be increasing from 2 to 4.5. And if you look at the graph that I just drew without actually knowing this, it actually increased from 2 to 4.5. And my derivative better decreasing from 0 to 2. And that's what we actually see from here as well. When my function concave up, it looks like a U, and that's going to be when the derivative goes up. When my function concave down, it looks like an N, and that's going to be when derivative goes down. And what about inflection point? If you actually see down here, the inflection point actually corresponds to the relative mean on my derivative. And that's actually what I have down here.